In 2009, a team of paleontologists was sifting through ancient rock deep inside the sweltering Cerrejón coal mine in Colombia. They were pulling out the compressed remains of a 60-million-year-old rainforest, but one specific find stopped them completely: a vertebra thicker than a human wrist. When paleontologists see a fossil that large in tropical Paleocene rock, they logically assume it belongs to a crocodile. Those were the undisputed giants of the ancient swamps. But the curves on this bone were wrong. The structure didn't match any crocodile in the catalog. It was a snake vertebra. Finding a snake of this scale forced a recalculation of the maximum size a reptile can reach before its own biology fails. To figure out exactly what they were looking at, scientists relied on a predictable scaling law. With modern constructors, the size of a single vertebra directly correlates to the animal's total body length. By scaling up from the Cerrejón fossil, we arrive at a creature over 50 feet long and weighing 2,500 pounds. When we place the largest recorded modern anaconda inside that outline, the ancient snake is nearly twice its length and 5 times heavier. If you placed a snake that massive in the modern Amazon or Congo basin, it would die. Today's tropical rainforests are too cold to support an animal of this scale. The existence of this snake requires a planet with vastly different physical conditions than the one we live on today. Snakes are ectotherms. They lack the internal machinery to regulate their own body temperature, relying entirely on the surrounding environment to stay warm. As environmental heat rises, an ectotherm's metabolism runs faster, powering the digestion needed to sustain a massive body. Running this biology in reverse gives a clear climate reading. Powering 50 feet of muscle required an average Paleocene temperature of at least 32 degrees Celsius. The world surrounding this creature was a relentless greenhouse, an incredibly dense tropical canopy stretching across continents, offering zero seasonal relief from the heat. That makes Titanoboa a biological thermometer. Its fossilized bones permanently record a period of extreme, unrelenting global heat. Dragging 2,500 pounds of mass across a forest floor is mechanically inefficient. Out of the water, gravity would compress the snake's internal organs, making breathing difficult and movement nearly impossible. Its actual operational domain was the network of slow-moving river systems cutting through the jungle. The water provided essential structural buoyancy, supporting its massive weight. In those tannin-stained currents, it behaved like a submerged ambush crocodile. It glided silently just beneath the surface, remaining perfectly still until prey wandered close. When it struck, biomechanical models estimate it clamped down with well over 400 pounds per square inch of pressure, enough force to instantly crush the shells of giant turtles. Its immense scale and crushing power were specific adaptations for surviving inside a swampy labyrinth during a hyperheated slice of deep time. Millions of years after the Paleocene, the Earth began to cool. The average global temperature dropped by just a few degrees. This chart tracks that cooling trend against the biology of the era. As the environmental temperature declines, metabolic efficiency plummets. The giant snake's digestion took longer, movement became sluggish, and its growth stalled. The surrounding ecosystem shifted. Humid swamps began drying into seasonal riverbeds. Massive reptilian prey dwindled, and warm-blooded mammals began outcompeting sluggish reptiles for resources. No apex predator hunted this giant snake to extinction. It starved in slow motion because its specialized biology was tied to a climate that no longer existed. A drop of only a few degrees on the planetary thermometer was all it took to erase the largest land predator since the dinosaurs. Climate serves as a strict physical boundary. It dictates the upper and lower limits of what biological forms are permitted to survive. Titanoboa was an animal that pushed those boundaries to the edge. It ruled the ancient swamps only because, for a brief window in Earth's history, the planet's conditions allowed it.